All right, so let's talk about performance. This is the first of a couple of lectures on performance, and we'll discuss how different designs might affect the performance. We'll work through a really simple example and consider different design decisions, right, and see how they affect performance. We'll see. First, we'll look at a very trivial solution to a particular problem and see that it doesn't perform any better. And we'll just tweak the design a little further and see how the performance improves up to the point that we might feel that it's good enough. And it turns out that when you zoom in further into the benchmark, it turns out that it's not any better really from our first couple of iterations until we finally find a fundamental. We fix the fundamental problem with our original design, and then we see that our solution is performant regardless of what the size of the problem might be. Okay, so we'll iterate a couple of these and see how they stack together, how they compare, and we see that the point that we're trying to drive is that the design or a particular solution does affect the performance. Yes. All right, so the trivial example that we're going to look at is something that we do all the time, right? We manipulate strings, we concatenate them, we put something together, and if it's just one string or a couple of strings, that's fine. But if it's something that you're going to do in a loop or you're going to do repeatedly multiple times, certainly this could add up, right? And in particular, the example that in our previous lectures that we looked at duration. And in duration, we were calculating a format, right? And there were a couple of numbers and strings that we were concatenating together, right? And it was a trivial example, and we want to revisit that. What would happen if we would have to calculate, thousands, hundreds of thousands of these things, right? In a loop, and we would like to iterate over these things, and how would it perform? If you have these many records that you have to iterate over, and how would that perform against multiple different ways that you could do it? So let's consider the bare bones problem of string concatenation. We'll look at how Java does it by default. We'll see that there might be better solutions on how to do it, and we'll see that if you do this in a loop multiple times, right, it could be really detrimental to the performance of the overall application. So on the bare bones, if you're concatenating a string, you might have an empty string at the beginning, and as you iterate over several characters or integers or whatnot, you're just iterating, adding one character at a time, right? So it would look something like this. You get the result string, and as you iterate over every single character, you build up the string by adding one character at a time, and you're concatenating these things. And this might seem very innocuous, right? How bad could this be? And also, what's wrong with this particular implementation? I mean, we have to loop, right? That's the bare bone implementation, is that you have to look at every single character, underneath under the hood. Right, the way you concatenate is you look at every single character, you copy it over, and you build a bigger string, right? And presumably, as you iterate, right, it looks like you're always doing the same thing, right? You grab the next character and you add it to the next one, and you grab the next character and you add it to the previous one. Looks like it's constant time work, right? That you're always doing the same thing, and you have to iterate over the entire list of characters. I mean, there's no way around that. You have to look at every single character. How bad could this be? Isn't this already the best that we could possibly do? And now without knowing what really is happening underneath, right? It might be that our abstraction of strings works against us. That it hides too much from us, right? That we don't really know what's going on underneath, right? We have this very convenient plus operator. That does the concatenation, and why bother looking any further? If we consider what actually happens under the hood, we'll look at it in a minute. But before looking at what's happening underneath, we can try and benchmark this and say, well, let's not look at really tiny strings. Let's look at really long strings, and also with varying degrees of formatting, right? In the format string, remember you can embed percent signs. That you can say %d, %s. You can do all sorts of embedding. Yes, and each one could have a varying degree of density of how many operations you're doing inside of a string. Yes, it could be maybe. So we could consider maybe perhaps multiple different sizes of a string. 1,000 characters, 2,000, 3,000, 4,000. So an ever increasing number of characters, and then perhaps we can consider different varying degrees of density of the the percent operator, right? Of how we're concatenating strings or digits or numbers or whatnot. Maybe we're formatting, we're padding zeros. So there's all sorts of transformations that we need to build all these strings. So if we look at different densities and different lengths in string, we benchmark it, and if we look at just for a density of 1/4, meaning 1% every 4 characters, right, or every 50 characters, or 50 of these per 1,000, we see that as we expect, the longer the string, the running time obviously increases, right? This is kind of what we expected. Same thing down here. It's a little more dramatic here when we have a higher degree of density of percentage formatting there. Notice that it's notice that it's perhaps even twice as big as the one above. That's to be expected. Yes, but really, what we should consider is the following: the thing that really should give us trouble here or pause is the shape of this curve, right? The shape of this curve, if you look at it, right, it looks like it's doubling every time, right? It looks like the next one is twice as much as the previous one. This one is twice as much as the next one, and so on and so forth. Even though, right, the input string are not twice as big as the input, right? The input, notice that it's linear, right? 1, 2, 3, 4, right? So the input seems to be growing linearly, while the performance is not growing linearly, right? So that certainly should be concerning to us, right? That it looks like whatever's happening underneath, the performance seems to be quadratic as opposed to linear, right? And we know that that should always give us pause if we have something that's exponentially hard, right? So something that might work fine with something that's small, right? It might actually not be performant on something that is twice as big or whatnot. Yes. So really the shape of this curve should give us pause, right? With regardless of the complexity, it looks like it always has the shape. We can even look at it in the numbers, right? Going from 1,000 to 2,000 more than doubles the time, from 80,000 nanoseconds to 300 nanoseconds. From going to 2,000 to 3,000, right? Almost more than doubles, and going from 3,000 to 4,000 almost doubles the previous one. Yes. Right, so that's really what's concerning, that it's exponential. So this perhaps was not to be expected until you consider what's happening under the hood. What's really happening under the hood. This is just pointing out what is worrisome, right? That even though the input is linear, right? That even though the string, if the string doubles, the output, the time that it's taking, more than doubles, right? So it's growing faster than the size of the problem, right? And that's fine. I mean, we know that there's a family of problems that are inherently hard, right? And there's not that much to do there, right? The NP versus P. You've seen that, NP versus P problems, right? We know that there's problems that we know are inherently hard and exponential, and we can't do much about it until we do prove whether P is equal to NP. Then we will know. We don't know yet. So we know that there's a family of problems that have that inherent problem, and we can't do anything about it. But certainly, string building cannot fall under that category of problems, right? So we certainly hope that we could do certainly much better than exponential growth, right? Time complexity. Hopefully, we can bring that down, that curve, from quadratic maybe to linear, right? And we've seen that there's this, if you've done algorithms, that there's some fairly fairly intelligent ways to deal with data. That the more you add metadata to the data that you're manipulating, the better performance you can expect, right? So we saw how we could bring things that are quadratic to linear to maybe log performance. Yes, the more you pre-process the data, the better performance you can get. So let's see if we can apply some of these strategies to these trivial example of building strengths, right? So hopefully we can do better, much better. So let's see, why is it that what is the fundamental problem of why this is not performing, right? First we have to identify what is it that makes this quadratic, right? So an inspection on the way Java represents strings gives us some clues on what's going on here, right? If you remember, Java strings are immutable, right? Meaning that once they're initialized, once they have the initial set of characters, you cannot modify them. You can't go in and modify the string. To modify the string, you basically need to create a brand new string, right? With new data in there, right? And we have all sorts of syntactic sugar methods that hide this fact from us, like concatenation, like the plus operator, right? It looks syntactically like you're getting the same string modified, but you're not, right? Basically, what you're getting is a brand new string, right? That has a copy of the original string plus whatever it is that you concatenated, right? Once you understand the under the hood behavior, then it starts giving you some hints of what's going on under the hood for the performance to be so terrible. Okay. Yeah. So the way string implements appending, right, is to allocate a brand new string, copy over the content from the old string, and then allocate enough space to be able to append the new string. Right, so there's a brand new allocation. There's a time that it takes you to copy over every single character. So it's much more expensive than just putting a new character at the end of an already existing string. Right. Also, in the particular case where you are concatenating every single character, presumably you're looping. Right, where you're looping through each character that you're copying over, and every time you copy a new character, you throw away the old string, you create a brand new one, you copy, and you allocate enough space to add a single character, right? And then when you're going to add a new character, you do the same thing. You throw away the old string, you allocate a brand new string, you copy over the old string, and you allocate enough space to add a new character. And you do this for every single character, depending on the size of the string that you're concatenating. Yes. So it's a loop inside of a loop, right? That gives you a hint why this is quadratic underneath. Yes. Yeah, this string is increasing over time, right? One character at a time, and every time it increases, you throw away the previous one and you create a brand new one to start off with. So very non-performant. Mathematically, we can certainly formally represent this problem as a summation of the sizes of the strings as they increase over time. A string of size 1, of 2, 3, 4, right, and it increases at a time. How many times do you do this? Right, well, as big as the string that you're concatenating. So you end up with something like this, right? N times n plus 1 over 2. There is a proof on the slides, on the lecture notes, right, that goes through why this is true. I'm not going to cover that, although there's a trivial one that doesn't involve so many steps. There's a really trivial one proof, but I'm not going over that. Anyway, but the resulting one, right, the closed form of this time function, right, indeed is it's n squared, right? N times n, you get a quadratic equation that tells you what to expect as a performance of in terms of the size of this string the time is quadratic, right? Yeah, so time is quadratic. Notice that we do have a constant over here, meaning that this constant takes into account that perhaps the same algorithm might perform better in a faster machine than it might perform in a slower machine, right? So there's constants involved in there. But even though it might perform better on a newer laptop than in an older laptop, an older OS, nevertheless, the only difference between them is some scale factor, right? It gives you the same shape, though, right? And we're more interested in the shape than the actual constant. You know, it's even obviously as machines have become faster and faster and faster, perhaps we're not as rigorous as we should be. And we throw at some of these fast machines some things that are very inefficient, and we don't bother to optimize this performance. But we know that we should optimize nevertheless, regardless of what the actual performance of the machine is. Really, we care about the shape of the curve more than we care about the constant, right? So the constant basically takes into account to say, well, this is a scale factor that takes into account that you have different machine size, right? Different infrastructures, different environments. Nevertheless, the shape is what we care about. That it's superlinear, right? It's more than linear. It's quadratic. The constant will come back to. We'll talk about the constant a little later, specifically because we'll look at two solutions benchmarked, and for the size of the problem, they will look almost as performing equally well, okay? But it'll be because we are way too zoomed out, right? That it's only because other solutions are so worse than these two particular ones that they don't even fit in the benchmark, in the graph of the benchmark, right? And zoomed out that far, we will have two particular solutions that almost look that they're equivalent to each other until you zoom in, right? And when you zoom in, it turns out that no, it's not any better actually, right? That it has the same shape, right? It was only scaled down by this factor, right? That it looked like it was better, but not really, meaning that for a large enough problem, right, the solution is actually non-performant, right? So we have to be careful that we always take into account what is the zoom factor, right, and the scale that you're comparing these things.